Let's now consider a real Joule cycle, that is a Joule cycle for which we take into account the possible irreversibilities coming from the imperfection from the technological elements we are using in this cycle, especially the compressor and the turbine. Both of them, compressors and turbine, are performing adiabatic transformations, and this holds true because we can reasonably neglect heat transfer during the compression and the expansion compared to the technical work that is exchanged during these two transformations. So we still consider these transformations as adiabatic, but we now need to take into account that there are irreversibilities. From an entropy point of view, the irreversibilities will create entropy, and the fact that there's no heat transfer means that there's no entropy exchange between the system, so the working fluid, and the outside of the system. So because there's no entropy transfer but there is entropy creation, there will be an entropy increase during compression and expansion. Let's try to plot this real Joule cycle on a TS, temperature and specific entropy diagram. So as before, we can first plot the two specific isobaric lines corresponding respectively to the low pressure and the high pressure. So these curves are going up, and we also can see that the spacing between these two lines is increasing when going to higher entropies. And I also plotted two specific isotherms, so isotemperature lines, which are corresponding to the lowest and highest temperature. Lowest temperature usually corresponds to the ambient temperature, and the highest would be the highest temperature that can be admitted to the turbine, so which is defined by technological consideration. So let's start with point A, the inlet of the compressor. This inlet of compressor is at lowest temperature and also at low pressure. So without surprise, point A will be somewhere there. Then how to plot what would be the outlet of the compressor. In that case, we will use an intermediate point which corresponds to the outlet of the compressor we would have if this compression was reversible. So for this reason, if it's reversible because it's adiabatic, there's no entropy change. So we can plot here the specific entropy of point A, and the intersection with the high pressure corresponds to this intermediate point that we can call here D is, like isentropic. And this B is point corresponds to the previous point D we had for the ideal Joule cycle. In our case now, because of the irreversibilities, the entropy has increased during this transformation, so we know that real point B is at high pressure but at a higher entropy, so somewhere to the right on this high pressure isobaric line. So real point B is somewhere there. So that means that the compression will look something like this. Next transformation is not much different than before. At high pressure, there's a heat exchange in order to increase the temperature of the working fluid up to the highest temperature. And so at high pressure and at the highest temperature, we have point C. And so we usually neglect pressure losses in the heat exchangers. So in that case, we can consider that it's an isobaric heat transfer from B to C. Then from C to D, similar thing that what we have done for the compressor. We first consider a reversible adiabatic transformation, that is an iso-entropy transformation, and so we can plot here the specific entropy of point C, and the intersection with the low pressure isobaric line corresponds to this intermediate point. D is for the isentropic expansion. In the real turbine, there is entropy creation that is due to the irreversibility. So real point D will be somewhere on this low pressure line, but to the right. Once again, so real point D is somewhere there, and we can schematically join point C and point D to show what took place in the turbine. And then finally there's the heat transfer with the cold source, which is at low pressure in order to cool down the fluid from point D to point A. So on this TS diagram we can already see a lot of things, because the compression and the expansion are both adiabatic. The difference of the technical work that is involved is directly equal to the difference of specific enthalpy across this transformation. And as we have seen before, in an ideal gas, this difference of entropy is proportional to the difference of temperature. And here we can already observe a few things. Between A and B, compared to A and B, is the difference of temperature has increased. So it means that now we need to provide more technical work for the compression. At the reverse, for the expansion from point C to point D, the difference of temperature is less than from point C to point D is. So the fluid is now giving less technical work to the turbine. And finally, the last thing that is really interesting here is that from point C to point D, the difference of specific enthalpy has decreased, because this temperature difference has decreased too. That means that there is less heat to provide from the hot source in this heat exchanger. Let's now look at how we can calculate the exact location of point B and point D in a new video.